But what this session is about is talking about Data 8, which is our first course. It's a freshman level course at Berkeley. It's where data science education at the undergraduate level started at UC Berkeley. And it's grown quite a bit since then. So if you stick around for the rest of the week, then you'll hear all about what else has built on top of it. But most of today really is about Data 8, what's in the course. You'll get to experience some of the student experiences. If you participate in the interactive lab, you'll get to hear about other instructors that have taught something similar elsewhere. But I'm kind of the warm-up act for the day, where I'm going to just tell you about why the course is what it is, kind of reflect on some of the design decisions, but also try to inform people about what the content of the course is and what the learning goals are. Yeah, I hope you'll interrupt with lots of questions. I can tell from the questions I've heard already that many of you are much farther along in this process of learning about how to teach data science than what I'm targeting here. But I will just focus on making sure that I give a clear introduction to what a first data science course looks like from our Berkeley perspective, for people who haven't taught data science before, aren't quite sure how it differs from teaching statistics, how it relates to teaching computer science, yeah, just talk about the decisions we made when we designed a first semester-long course. So I hope that's interesting. If you know the course already, you're certainly welcome to stick around and ask questions, but I might not tell you too many things that you don't know already. And I'm John DeNero. I helped design the course with Ani Adhikari and David Wagner, though actually we got input from all around campus. Tab Parikh helped a lot, Michael Jordan helped a lot, David Culler, Catherine Carson in the early days, and then it just grew from there. We've had tons of faculty, students, staff from across campus contribute to the course in various ways, and it has grown in wonderful ways since the original design. So I'll try to tell you about some of that, but most of this is about what we came up with when we tried to build the course in the first place. So before I go on, I'll answer two questions from the chat. One is, do you see advantages to using Jupyter versus Colab? They're becoming more similar over time. I think Jupyter gives us a little bit more control over the environment. So for example, we can have buttons on the website that open up to exactly the page that we want within Jupyter. And it's all nicely integrated with our auto grading scripts, and so people can submit their work afterwards. So there are some small advantages, I think, to running your own hub, but I don't think they're huge. And another question I see in the Q&A is Data 6 the new first introductory course before Data 8? Data 8 is still a course that doesn't have prerequisites, and yet it pushes students reasonably hard, and therefore there can be great benefit to having some of the ideas presented in a different way, at a different pace, and in order to help people kind of get ready for Data 8. I do not think it's the case that Data 8 has somehow morphed into a very difficult intermediate course that can't serve as a kind of first introduction for college students. But college students come in with a lot of different backgrounds. There's a lot of variability there. And so it does make sense to have kind of different courses for people looking for a different pace. And so that's what Data 6 is about, is making sure that there's an onboarding path for people that might otherwise find Data 8 intimidating. And for someone who can use help installing the littlest Jupyter hub, I don't know if there'll be a session on that, but I will pass that along and see if I can get you an answer sometime. Okay, so let's dive in. First, what is this course that I'm talking about, Data 8? First, where are my slides? Can't have a presentation without fumbling with the slides a little bit, right? I want to make sure I can see the questions and I can see my slides. I can. Okay, beautiful. So the idea of the course was to describe how data-driven reasoning should be carried out now that programmable computers are the primary tool for any kind of statistical inference or inquiry. So that's where computing and statistics met. Statistics is a very important discipline about understanding the world through data. What do they use as their tool? Well, not so much a hand calculator anymore. Instead, a programmable computer is more useful, and we want to present that. A very simplistic view of what we've done is said, what would a first statistics course look like if you assume that computers exist and students could learn how to program them, as opposed to earlier designs that were more focused on hand calculators and back in the day when you wanted to draw a sample from a distribution, it was a lot of work. Now a computer can do it for you right away. But that's not the whole story. I think that there are really three pillars. There is a computing pillar that is really about introducing people to computing and programming in a way that's fundamentally different than what computer science courses do. Because computer science courses are typically about building stuff, creating artifacts, making games, making art, making music. And instead, in Data 8, we only focus the computing on how to understand the world using the computer as a tool. Which, I think that's just engaging for a set of students that have different interests than those who just want to build apps. There's lots of students who want to do both, but this is a different perspective on computing. It is absolutely a course about statistical inference. It just seems like as we're awash with data in the real world these days, people need to understand things like what happens when you take samples, what can you learn and what can't you learn, how can you make robust conclusions based on kind of limited information. So the field of statistics, I think, it's a relatively new field, just like computer science, but it has changed over time in that it's kind of taken on computing as a fundamental tool. And we want to show how that's done. And then the third part is about using real world data and real world examples. So I think this is important because it makes the content matter to students. It's also important because then it's very natural to consider human context and ethics questions as you introduce the technical material. And these really need to go together. I think it's not a good idea to educate students on how to, use computers and how to use statistics without them understanding the implications of doing so on the world in which they're used. And so, so real world examples allow us to, have questions drive the content, and also allow us to constantly layer in some ethical questions and just reflections on what the data mean. Which I think is fundamental to data science. Oh, I've rambled on for a while. I haven't even gotten on the first slide. What am I doing? So I figured I'd start with something that I think is different about this kind of course, rather than just teaching a statistics course, which is that we often give students an entire data set that might be publicly available and have them go through the work of summarizing it into a visualization or some summary statistics, as opposed to giving them just a table of the summary statistics and asking them questions about that. And we really want to push students to understand, given that they began with a raw data set and they perform some manipulation, like what information is still there in the product that they generate, the visualization or the analysis, and what has been lost, and understand the process that went from kind of just something that wasn't the data set they wanted into the data set they wanted in order to run their analysis. So first day, first lecture, we talk about text data, and we do an analysis of the text of Huck Finn and of the text of Little Women as an example. So two classic texts. If you haven't read Little Women yet, I'm going to spoil some of the plot, and that's just too bad for you. You missed your chance to read the whole thing yourself, or you can plug your ears for the next couple of minutes. But we want to shift students from thinking about computers can somehow understand everything there is about the data in the way a human would, to really having them focus on what computers are useful for, which is often identifying patterns, helping people focus their attention on what's important and what's not. And text is a great way to do this because there's lots of different manipulations you can perform on text, but the questions you ask in a data science context tend to be different than what you ask in like an English literature class. So we're not asking about, what are the themes and how they shift over time in Little Women. That's just not something that through kind of elementary manipulation with a computer you could get at. But we can answer the following question, which is, Who is the book about? So the kind of final example on the first day is to generate this data visualization, which shows for each chapter in the book Little Women, how many times has each main character been mentioned so far in the book. And so these are a cumulative number of times each name appears. You can see from this who's kind of the protagonist. It's Jo. So Jo, Amy, Beth, and Meg are sisters. Lori is the boy next door. And we generate this visualization just to give students a sense of how to go from text, which has lots of complexities, down to something that's just sort of like simple enough that you could recognize an interesting pattern in it. And then we pose the question, Lori is a young man who marries one of the girls in the end. Can you use this plot to figure out who it is? I'll give you a chance to look at the plot if you haven't before. And maybe you want to share in the chat what you find. And while you're thinking about that, a chat question was, what about the racial context in Huckleberry Finn? It's a great question. Since all we do is count the number of times the particular characters were mentioned, we don't actually engage much in the kind of historical context there. But it is something that's worth thinking about, and it would be very reasonable to kind of present your perspective on that book if you're going to talk about it, or you could skip it. Okay, so some people said Amy and some people said Jo. I will say that you can tell from the chart that it is Amy and Lori who get married right around chapter 35, because you can see that whenever one is mentioned, the other is mentioned. So there's a little zigzag part where they're both mentioned together, and then a chapter goes by when neither of them are mentioned, and then they're both mentioned together. It's Amy and Lori and Amy over and over again. And that's why you see their two lines moving in lockstep, true love in a graph right there. So I like this example because it's not so simple as just looking at two bars and saying, oh, this one's taller than that one, so we're done. Instead, it illustrates the fact that sometimes visualization can convey quite a bit of information and can allow you to explore a data set even if you don't know exactly what you're looking for at the beginning. And that, a good visualization can sometimes answer questions without having to run some statistical analysis and make a lot of assumptions. So this is the kind of thing we would like students to be able to do. And that's why we use it on the first day, is they would like to take a data set that isn't prepared for them very much. It's just the kind of thing they might find on the web. And transform it so they can get a visualization to look at whatever aspect of it they think is interesting, and then draw conclusions from that. Okay, so that's where the course begins. I'll follow up by answering a few questions. The questions about prereqs. We don't have any prerequisites for the course. Especially in computing, we were very explicit about saying that this should be a course where students don't have to have prior programming experience. And we've collected a lot of feedback. And there are definitely students who say, oh, I wish I had programming experience because these other students had it. And the course was easier for them. So, but there are also many students who say this is a very reasonable first course in programming. I came in with no programming experience and I was able to learn it all. And I would say, I'm not surprised at all that there's some variability on that question, but this is not an unreasonable kind of first course in computing. We've made a lot of careful choices about where to make things complicated because it's important for the instruction, but then where to keep things simple in order to make sure that there's a low level of frustration with the programming elements of the course. I'll talk a little bit about that in a minute. And then as a statistics prerequisite, the high school math curriculum is going to include exposure to, means and standard deviations and even histograms, but we don't assume a whole lot of that. Instead, we do spend quite a bit of time just kind of studying histograms from scratch, even though they're meant to have known it in high school, because we find that there's a lot that students can learn about interpreting data visualizations when they see it in a context where they're controlling exactly how the data visualization was constructed and answering rather sophisticated questions about it. And yes, Ksenia raised a good point, which is that we do expect that they've kind of completed high school math curriculum. It doesn't require calculus, but algebra 2, yes. Okay, let me just peek at the Q&A, because see if I'm keeping up. Handing a students in a data set and having them do visualizations and summary stats is something we do in our elementary statistics course. What makes data science different? Size and source of the data sets. There can be lots of overlap between how a data science course works and how a statistics course works, and that's okay. I think that once I talk through how we cover statistics, you'll see that we spend all of our time on sampling-based inference, which tends to be different than exactly what happens in a typical intro stats course, but there are lots of different stats courses in there. So I wouldn't be surprised at all if someone took this curriculum one day and said, well, this is a statistics course. I'm going to label it as such. At the same time, there is more computing programming content in this course than I've seen in typical introductory statistics courses, because we walk through, I'll talk about it in a minute, but we walk through a fair amount of how to manipulate tables. We do joining and groups and the kind of stuff that you might see in an intro programming course, and a fair amount of defining functions and understanding why. So maybe the programming content is larger than what you'd see in a typical statistics course. And maybe the way that the statistical inference is presented is different. Yeah, and there's kind of unique aspects to data 8 in the way that we cover human context and ethics. The classification unit at the end, I think, is a little bit different than what I've seen in statistics courses in the class. So there's nothing wrong with reacting to what you've seen so far and saying, well, this is a statistics course. It does fulfill the statistics requirement for many majors and minors across campus. So from that perspective, yes, it's just teaching you statistics, but it's doing it in a different way. What do we learn from the totally flat part of Amy's graph just before the lockstep starts? What you learn there is that the book was not talking about Amy, it's talking about somebody else. So I think Joe has to go off to New York and fall in love with a professor or something like that. So yeah, I suppose there's kind of a wonderful exercise to go through with students live, is to talk about different parts of a visualization and what they mean. I think we do this most with histograms, because there's lots of ways to be misled by what's in a histogram, but you can certainly do it with a cumulative line plot like this as well. I've seen the page for the first lesson and the complex code displayed. Can you talk about why you decided to show it on day 1? It is the case that in this course, we have a first lecture that doesn't explain all of the programming, and then the programming is kind of built up bit by bit, and lecture 2 doesn't have any programming at all. It's just about statistical reasoning. So it goes through the John Snow example, if you're familiar with it. If not, you can read the book. But the choice to expose students to what a program looks like without explaining it all to them on the first day was an intentional one. It's one that I tried before Data 8 in the introductory programming course, and I like the effect that it has, which is, even though it leaves students with a sense of wonder because they saw some code on the screen that they didn't understand, it does expose them to the potential or the motivation for why they're writing these programs. So you get a little sense of programming is kind of like structured text, except for there's lots of dots and parentheses, and I don't know what those mean yet. But there isn't so much of it that I couldn't read it like I learned to read a paragraph, and you can see the outcome. So this example was chosen because it's just interesting enough to get people's attention, and just simple enough that the code doesn't go on for pages and pages. Now, of course, one could claim that it is very complex. Complexity is kind of in the eye of the beholder, but we did try to aim for something that was beyond what students would understand, and at the same time wouldn't kind of turn them off from the whole subject and say, oh, I should go take a different course. And whether we've struck that balance perfectly, I don't know, but it seems to resonate with a lot of students. Okay, someone may have been referencing is, do you address ethical coding and bias within some data sets in Data 8? Yes, I'll talk a little bit more about that later. We're actually talking right now about how to increase the amount of human context and ethics, data ethics content that's in the course, because there's just a lot that's changed in the world since this course was developed in 2015. And so I think there are opportunities to do more, but it has always been a component of the course to talk about ethics, so bias. One thing in particular is when you choose what to measure, what information do you lose about the world, what biases does that introduce, and then there's a lecture on privacy. So there are some kind of classic data ethics topics embedded in the course, but we also just try to bring this up whenever it's relevant based on a real world data set that comes along. Has this class been taught at an accelerated rate, such as in 4 or 6 weeks? We teach it in 8 weeks over the summer, and most students are taking just one course at a time, or maybe 2 courses at a time. So yes, that's been done. Okay. I'm going to jump forward a little bit, and then I'll go back to these questions. So let me talk about the course design. I've mentioned this a little bit already, but what's the story with the computational thinking or programming part? I know computational thinking is kind of a loaded term, but it seems useful in this context just to say that we do want students to understand that they are able to program computers to do whatever they want them to do, and that is an acquired skill that requires practice. We do, however, want to have no programming prerequisite. And so we have a much narrower set of learning goals around computational thinking than a typical introductory programming course. There's lots of content in introductory courses in computer science that is not in Data 8. We really just want to select a little bit that's relative to data-oriented inquiry and is something that is manageable enough that most of the course can be about statistical inference. So what is it that we try to convey? I think if I had to summarize it, I tried, it would be to use computation to automate repeated tasks and to learn how repetition is useful for reasoning and inference. So let me give you some examples of this. We teach them how to define functions and apply them to many values. So the story within Data 8 is usually something like this. They pick a state, California, and then they get the population by looking in a table of populations and finding the rows where the state is that state, and then they do some manipulation with it. And we want to make sure that they understand that any piece of code can instead serve as a template where you can abstract away the constants that you defined in the beginning as arguments to a function. So they define functions like this all the time. And we do actually teach them to get there by focusing on a particular example, getting their code to do what it wants for the state of California, and then write the function that generalizes it, which I think is different than how we teach functions in introductory programming courses, which I also teach. It fits well with the goals of data manipulation, I think. Just to say, functions are there in order to allow you to repeat some process that you've defined for a particular case on other similar cases. We do teach iteration, but never to write an algorithm. They're never writing a sorting algorithm. They're never, finding the second largest item in a list or something like that. Iteration is really there just to do something many times. And so you see lots of examples in the course that say, 1,000 times draw a new sample from some table, which may be a sample itself, or maybe some representation of a whole population. And then what do you do with that sample? Well, here we're appending it to a list of means. This is as far as we go with iteration, it's an important first step in understanding how a computer can do a bunch of work that you specify, but you don't carry out each step. The computer does that. But it's nowhere close to what you see in an introductory programming course, which is about using iteration in order to solve novel problems that are fundamentally computational. That's not what Data 8's about. And then there's a fair amount about the effective use of modules or libraries and objects. So here, the repetition is really you taking advantage of some procedure that has already been defined for you by somebody else, which is mostly how computing has become so productive in the modern era. So students spend a lot of time constructing compound expressions based on understanding the primitives and figuring out how to fit them together. So here's an example from the course. What's the average salary of an NBA player who is more than 80 inches tall? And so they have to know that, this is a table where you can filter its rows. Here's the way you do it is that you pick which column you're filtering on and you construct a predicate. Now you have another table, which means you can get its column. Now you have something that you can compute the mean on. So there's a fair amount of understanding different data types there. What's a table and what operations can you do on that? What's a array, which is what we use to represent a column, and what operations can you do on that? And understanding how some of these different operations are built into different parts of the programming environment. So some of them are part of NumPy, and some of them are part of the tables module that we give them. And they have to understand that, like, oh, if instead what you want to do is draw a histogram, you have to do it in a slightly different way. So, now I'm down in the weeds, which happens sometimes, but I just wanted to show, like, students do have to be aware that there might be, two different methods that take the same arguments, but they return different types of values. So this one returns an array that you can take the mean of, and this one returns another table that you can draw a histogram over. So these kinds of, like, thinking about data types and thinking about compound expressions is really one of the more important goals of computational thinking in the course, that helps students understand how programming languages work in a way that isn't really Python specific so much. It's meant to be pretty general, and gets them in the habit of going from whatever table was given to them to the table they want in order to draw the visualization they care about. We try to keep the programming simple to let the data motivate. So it's okay if the only for loop you ever write is do something for 1,000 times, as opposed to a more interesting for condition, as long as the data set that you're manipulating is actually describing something about the world that students care about. And we wanted to keep the set of programming topics small so that we could provide a lot of practice, and students would have a chance to master this small set of computing topics so that they'd be ready to go on and take a richer programming course later. Or if they've taken a programming course before, well, then they get to practice this particular subset a lot. And I've seen some questions already about how we do this. Jupyter Notebooks, we do use a particular module that was designed for the course, written first by me and then revised a lot by David Wagner. This is one of the controversial parts of our design. Why don't we use the industry standard tools? And I'll tell you, it's because if you wrote this same thing with the standard Python libraries, then there's like lots of nested square brackets, and understanding the type of each object along the way is just harder. So there's more overhead to using Pandas, which is kind of the typical industry tool, rather than using the version that we designed for the course. So it's always a trade-off. You don't want to just like teach people things that only work within the course. But since this is a public module, students could go use it in their internship, and they certainly have before. And so it's not a crazy thing to teach them that. And then we give them a lot of automated feedback in all their assignments. So if you want to learn about that, go to the interactive lab that's next, and you can learn all about it. Okay, I made it through another slide, which means I'll go check the Q&A, see how we're doing. Thanks, folks, for following along. Data 6, data 8, and even data 100 seem to focus on stats and computing. Where's the math? We do have a probability course, probability for data science, called Data 140 on our campus. And it's a math course that happens to use the same kind of computing environment in order to illustrate some of the mathematical concepts. So it's certainly there. We also do require linear algebra and calculus as prerequisites for these courses. So they do take math courses, but we do have one sort of dedicated math course. And then if you stick around tomorrow, you'll hear about a new course, Data 102, which is quite mathematical. It's still a kind of computing plus statistics course, but it relies on them having taken an upper division probability course, and it leans on that pretty heavily. And so there are proofs. Is it possible for naive instructors to audit the classic cal? We do have the online course, Data 8X. You look that up, you should be able to find a way to go through the entire course on the edX platform. Is this Python? Yes, it is. Do you abstract the relational algebra from the Python syntax? We do joins and groups, and we draw some visualizations of those things, and then we show them Python syntax for it. And do students really understand that the relational operations could be expressed in a different way in a different programming language? I think usually that comes later. So we set them up to understand that, but I don't think we really push it in Data 8. Yeah, Mark asked, why are we doing conditionals? I assume you're asking about the dot where with the R above 80 part, as opposed to lots of square brackets. Yeah, we found that square brackets really do cause a lot of trouble, because in Python, the way square brackets are used can mean a lot of different things, and especially in the NumPy and Pandas libraries. So if you really want students to be precise about, like, what's the type of this sub-expression and why is it therefore a reasonable argument for this larger expression, then I think it's a little bit easier to do it within data science rather than Pandas. But I'm sure people will try it the other way and find some success. But that's why we came to this conclusion of writing expressions in the way that they did. We make sure students understand parentheses and dots and names and literals, strings and numbers and things like that. But we don't try to help them understand how operator overloading works, because that's quite an advanced programming concept. What makes doing the teaching coding this way better than, say, using R? I don't think this is better than R. I'm sure that you could execute something very similar in R. I think that when you pick a programming language, then you have to decide how to introduce that programming language, what to keep, what not to keep. So the same set of decisions would have to be applied if we had picked R as a programming language. And I hope that we would come up with basically the same result. But of course it would look different because the syntax is different and there are different built-ins in the language. But I don't have like a horse in the race of should students learn Python or R. I think both are totally reasonable. In Berkeley, there is a nice synergy between Python being used in this course, it being used in the introductory programming course, and it being used in the introductory signals and systems course. Lots of students take all three, so they really do kind of build mastery by seeing the same thing over and over again. That said, you don't want them to just get locked into one programming language, so lots of our students learn R as well. I see a mention of a course called Data 100. What is that? Where is it in the curriculum? If you want to learn all about that, you'll mostly have to stick around till tomorrow, where the instructors and creators of Data 100 will give a description of it. It is an upper division course, meaning our students take it in their junior year, typically, and after they've taken Data 8 and programming course and a linear algebra course and often some kind of lower division probability course, and then they take another data science course. So it's just like the next step in the curriculum. Okay, thanks so much. Let's talk about inference. The motto of the course is visualize, then quantify. Well, first, actually, let me back up and say that the sort of structure or arc of Data 8 is to motivate programming topics by inferential goals or questions that you would have about the data. So it's front-loaded in the sense that there's a fair amount of programming up front, in order to get students comfortable with table manipulation and drawing visualizations. But yeah, but it really is the inferential questions that drive the course. We pick a data set, what questions we want to ask about it. What do we do next? Well, maybe we need to learn some programming in order to do it. That's kind of how we keep things moving along. And from the point of view of how you answer questions with data, we really do try to push a perspective, which is that you want to draw a visualization in order to understand what's going on. If you see a difference between two quantities, then it might be worth quantifying. You could run a hypothesis test. You could compute a confidence interval. You could try to figure out, are these different because of chance, because this is just a random sample, or is there like really a underlying difference here in the population, and how might we reason about that? But that quantification comes after just making sure that you can understand what the data represent, perform the manipulations that you need in order to summarize it in a useful way, which is more often than not a data visualization, though sometimes it's just summary statistics. And make tentative statements about that. What do you see in the visualization before you jump into a hypothesis test? So the first unit in the course from an inferential side is about description and visualization, where many questions can be answered with a carefully crafted picture. Then, that takes, I think, 4 weeks or so. We move into chance. So we introduce probability, models, hypothesis testing, inference, primarily about, how to compute a confidence interval, but then why would you do this? What does it mean? And the primary tool for inference in this course is to draw new samples and see the difference. So we do try to steer away from, well, I would say we steer away from equations. We steer away from kind of anything that has to do with asymptotics. And so some of the classical topics that typically show up in an IntroStat course just aren't there. And instead, everything is about simulation, just generating samples either from populations. So we'd ask questions like, is this particular observed sample look like it's a random sample, like a uniform random sample from this population or not? And then we eventually get into the bootstrap. So that's kind of our primary inferential tool for once you have a sample, what can you say about it? Then there's a unit on correlation, prediction, and classification. We try to keep the techniques really simple. So simple linear regression, there's no multiple linear regression, just like one input, one output. And yet we spend, a week and a half, no, probably 2 weeks on it. To make sure that people understand, what you can and can't do when you draw a line. I'll talk a little bit more about that later. And classification. So, machine learning is obviously a hot thing. We want to give students some exposure to that, but we don't do it by teaching them a bunch of different classification algorithms. Instead, the only classification algorithm we teach them is nearest neighbor, or K nearest neighbor, to get slightly more sophisticated. But there's a whole lot more that we could teach. We just reserve it for a future course. Instead, in this course, we want them to understand the fundamentals of what does it mean to make predictions? Why do you, hold out data sets? What does computing the accuracy of something mean on a held out data set? Just try to get them to describe what they're doing correctly. Right, so there it is on the slide. Throughout, we would like people to draw precise conclusions stated in plain English. So there is a little bit of jargon, they learn what a p-value is and what a confidence interval is, but we would really very much like them to be able to, on the spot, define these things in a way that makes sense to them, not just describe the definition by memorizing it in a textbook, but, be able to say like, oh, yes, this is, well, I'm not gonna try to give examples because I don't have enough context, but I think we often go through in particular data sets and say like, okay, we computed the result of this hypothesis test. Here's this p-value. What does that mean? And have them talk to their neighbors about describing the conclusion not just to say like, oh, we reject it because some professor told us that the null hypothesis can be rejected now, but instead describe the reasoning from scratch about why you might make one conclusion over another based on some p-value that you computed. This shouldn't sound new for anyone who's taught statistics before, but just wanted to kind of lay out what we hope to achieve in the course. Okay, back to Q&A. For students interested in digging deeper in understanding the code, what do they do? I think the answer is that they take subsequent courses. A lot of our students take an interprogramming course at the same time they're taking this. So then, lots of computing material, and sometimes they take it just afterwards. Where do you see data science in the next 5 years? From an undergraduate education perspective, I would expect this to become very popular because we're seeing it happen already. And I think it's well motivated. So I think that students are understanding that they shouldn't just prepare themselves for their first job out of college, but they should kind of set themselves up for an interesting career. That career is going to overlap with computing, basically, no matter what industry or nonprofit or government work that they do. And therefore, they need to understand, what programming is all about and what computer-driven data analysis is all about. So yeah, I expect that there will be a continued interest in this stuff. And what about the actual content that we deliver? I'm not sure whether students will come in with radically different experience levels 5 years from now than they do today. I would expect that since there's a lot of effort to put computing at the high school level, that there will be kind of more programming experience coming in. We're already seeing this trend. But will they become more proficient in statistics by the time they show up in college? We'll see. I would love that to be the case. But I suspect that at the college level, there will still be a real need for kind of talking about what it means to try to draw conclusions from partial information and how to do it, what works, how to apply it to new situations. And so, we do that in Data 8 and in Data 100, which is the follow-on course, and in Data 102, which is the kind of advanced decision-making course. It even shows up in the probability course a little bit in examples. I think what's going to happen is that same style of teaching is probably going to move into lots of different disciplines. An exciting program at Berkeley called the Connector courses, which are small courses, like little seminars that students take concurrently with Data 8. And they're offered by people who are using these techniques or these ideas in particular areas, whether it's linguistics or public health or history. Whoever is doing the kind of data-driven inquiry in that department will often sign up to teach a seminar course where they don't have to teach linear regression. The students learn that in Data 8, but they can show how it's used in their discipline and why it's valuable. Or if there's particular technical content that's different from Data 8, then they teach some of that. I would expect lots more courses like that to appear. And because computing is transforming so many different academic disciplines, that the kind of structure of a university will be that there will be a data science core like this one, but then there will be lots of other courses that leverage that content in order to show people how this discipline works in the modern world. Are these slides going to be shared on Slack? Yes, I emailed them to Eric, so he will eventually get that email and post them. Maybe I can get you a link right now. In the chat of this session, there's now a link to the slides. Okay, the third pillar, teaching with real data. This makes it so much harder to build a course, but it's so worth it. So the idea we had, and I give Mike Jordan a lot of credit for this, and he's giving a talk tomorrow morning. So if you want to hear his perspective, please join. Was that we should just pick a problem and then introduce the technical concepts in order to make progress on that problem. And that problem should be real in the sense that it is something that occurred in the world and is therefore something that you could investigate by downloading some data that was collected for the purpose of studying this problem and study it ourselves. So computing and statistics come together in order to actually make progress on a real world problem. I prepared a bunch of these, but I'm running out of time. So we'll see how many we get through. But if you read through the textbook, which is at inferentialthinking.com, throw that in the chat too if you want to find it. You'll find that there's lots of real world examples embedded in the course. We use them in lecture. There are even more that show up in the labs and homeworks. And we've found that, arrays, tables, visualizations, inference, regression, classification, they can all be introduced with real world data sets, which takes more time because you have to describe the data and not just say like, oh, assume you have a table of numbers. Let's see how we'll manipulate it. But instead you have to describe, what these data represent and what changes about that representation when you perform some manipulation. But that is actually the skill that we would like people to pick up in this course, is to understand that, all these technical tools are only really useful if they answer the question about the world that you wanted to answer in the first place. And you have to keep track of what you measured originally and what about that measurement was maintained or lost as you perform data manipulations in order to come up with any conclusion that relates to the real world at all. And the human context and ethics of data become natural to focus on when there are real world examples. And in fact, students will call us on it if we don't spend enough time on talking about the human context and ethics, which I think is great. They'll say like, the data points in this data set represent real people, and you're not telling us anything about those real people or why they have these particular characteristics. And they should be saying that because that fundamentally, when you're answering questions about the world, understanding the context of the world, it helps you understand things better. So very natural to ask, how are the data collected, why they were collected, what bias might be introduced based on that, what information is lost during data collection. So for example, a lot of data sets, including the census, only use binary gender. And so information about real people who don't just fit into those classical binary categories of male and female is lost whenever you kind of force the data collection into something that doesn't accurately describe the world. And you just got to talk about that. And you wouldn't maybe do it if you weren't using real data sets in your examples, but you have no choice but to do it when there's real data involved. Yeah, we do a lot of geospatial visualization because it draws pretty pictures to like draw a map of the US and look at, different educational outcomes or income levels or public health metrics or whatever. But there are always associations between geography and race in the US. And so you just end up talking about that when you're working with real data sets. So I think it's a feature that makes the course harder to teach because you have to learn about the data sets. Harder to build because we had to find the data sets. And I think that's an ongoing process. They'll probably continue to be revised. And slower because you have to spend time on all of this stuff. You can't just crank through a bunch of mathematical content. But it is the way in which I believe data science should be taught, so that when students go out into the world, they're not learning for the first time how to recognize that a data set wasn't measuring the right thing in the first place. Instead, they've seen that kind of thing before when they were in college, and so they're primed to look for it. So I'll just flip back to the Q&A real quick. When teaching with real data, where does data cleaning, data pre-processing come into the curricula? We push that out to data 100, where there is a lot of data wrangling and cleanup. And data 8 is in a idealized and false world in which every data set is complete. There are no missing values. The dates are all formatted correctly. And that is a lie. We do admit the lie to students in the course, but I don't think they appreciate it because they haven't experienced the challenge that is kind of data wrangling and cleanup. That comes later. And the reason we push it later is that I think that the kind of essential lessons in data 8 can be illustrated just fine with data sets that are already tidied up. And the data wrangling component, learning what a regular expression is, it's all core material, but not necessarily a perfect fit for a first course, where we really just want students to focus on kind of the interpretation of the work that they're doing. And so we give them much cleaner data sets than they will encounter when they go out in the world and try to study their own problem. When selecting data sets, do you know ahead of time that a selected data set was used to provide specific insight, or do you analyze data sets to find something interesting, useful for the narrative? It's a mix. Some of the data sets in the course have been used to teach hypothesis testing for decades, and they just happen to illustrate it. Or linear regression the same way. It turns out that if you just download random data sets and draw a scatter plot, most relations out there aren't perfectly linear. And so it is the case that we've done some data set selection in order to motivate the topics that we want to cover. But when we present it to students, we start with the data set and say, oh, here's an interesting data set. Let's talk about what questions we would want to answer. And lo and behold, when we draw a scatter plot, it has that nice football shape. You could draw a line right through there, and it wouldn't really have to be a curvy line. It could be a nice straight one. I guess in the construction of the course, the topics really drove the data collection. In the presentation of the course, it's the data that motivates the topics. I feel like you're really getting a backstage view here. Don't tell the students. Okay. Well, I have about 9 slides worth of content highlights. I'm going to crank through some of them and just tell you some of the things that we cover in the course. Table manipulation. I've mentioned this many times, but we really do want to give them a full array of relational operations, selecting, filtering, sorting, grouping, joining, and lots of arithmetic. So you have these 2 columns and you want to combine them into a new column. But we want some interesting data insight at the end. Here's one, which is, if you look at the US Census data, and you force everyone to be either male or female according, I think, to their birth certificate, and then you look at a particular year, 2014, for every age, what's the ratio of 80-year-old females to 80-year-old males? Well, it turns out there's 1.3 females for every male, because men, they don't last as long. And isn't it fun to see that as you get into the older ages, this ratio changes? But actually back here, it was below 1, because slightly more male babies are born than females in the US. So, I don't know whether you find this interesting or not, but this is the goal. It's just to pick some real world data example that is relevant to the kind of academic material you're trying to teach. And then let the data kind of keep people interested. We spend a lot of time on histograms, and we do something that's genuinely difficult for students to grasp, which is to transition from measuring counts on the y-axis to measuring density. This is basically to set them up for future probability courses where you'd see a density function. Now, of course, the histogram is just made from a bunch of discrete points and has a fixed set of bins. But by measuring density, you kind of get the right effect when you allow bins of different sizes. So here's an example, is that there's a bike sharing program in San Francisco, and they published all the data of which bike borrowed from one place and where it was returned and how long the trip was. So this is a histogram describing the duration of a trip in a bike share program. And it's actually the same data presented in 2 ways. So there were a lot of different bike rides, so you can draw a histogram with a very small bin size, which is nice. This is something you need a computer to do. And here's the density scale that we want to give them is percent per second, which the students find as a crazy unit. Maybe you find it as a crazy unit, but the idea is that if you compute the area here, then you can get a percent of the total data set. So, this is 0.1% tall and about 150 wide, which means that this bar represents like 15% of all the examples in the data set. We try to teach them about that reasoning and to show that if you pick a different set of bins, you're still measuring on the same scale if you're measuring density. So like you're seeing the same numbers here as you are here, even though the bins are really narrow. Whereas if you were measuring counts, then like there would be a lot more counts in this bar than there would be in this skinny bar. So this is a technical topic, which I think is, not the easiest way to present it, but perhaps worthwhile in setting them up for understanding probability later on. We talk a lot about distributions. Oh, slide full of text. If you want to know what we cover in probability, you should read this slide. We do cover addition rule, conditioning, Bayes theorem, the normal curve, but there's no random variables and there's no other distribution families other than the normal. So it is a very limited introduction to probability. There is a connector course that covers quite a bit more probability, and then there's an upper division probability course that does the math in a more serious way. So you need some, but data 8 is definitely not. It's kind of the minimal amount of probability in order to understand what's going on in the statistics. I mentioned confidence intervals earlier. Here we use the bootstrap. So we begin with the observation that the empirical distribution of a large random sample typically resembles the distribution of the population from which the sample is drawn. It's a beautiful idea underlying the bootstrap. We draw a lot of pictures like this and we make them generate it to say like, oh, if all you're given is the sample, well, that came from a population. And since it's a large sample, its histogram probably looks like the population's histogram. Not exactly, but pretty close. And so if you draw more samples through resampling, then you're going to get things that resemble what you would have gotten if you had sampled from the population, but not exactly. And you kind of like work with the reasoning from there. So, this is a major technical topic in the course. Why is it there? It just seems like a fundamental idea if you're reasoning about populations from samples to understand what a confidence interval is, but we want to give them a way that is easy to visualize. And so we're leveraging computing here in order to give them a better chance at understanding what confidence intervals are. I will say my own personal experience is that teaching it with Bootstrap has made me more comfortable with the topic than I ever was having taken statistics courses when I was an undergrad once upon a time, before I ever kind of learned about sampling or simulation-based techniques. Linear regression, I think, to a classical statistics textbook by Friedman, Pisani, and Purvis, where we start with correlation as a descriptive statistic. Then we talk a lot about the properties of the regression line, how you would use it for prediction, what assumptions that involves, what's the regression effect. All that comes before the equations. So the stuff that the students who really like math get excited about with linear regression is like, what's the objective function and how do you minimize it? And oh, now we want to fit a quadratic instead of a line. Like, how would we do that? It's in the course, but it's pretty late. Most of this is about interpreting what you're doing when you draw a line. What can you do with it and what can't you? Making precise statements rather than just focusing on the math. And then we spent a lot of time on diagnostics and properties of residuals. So should you even be using a linear model for a particular data set or not? And just by looking at kind of the difference between the line you draw and the actual observation, those are the residuals. Anyway, we spent a lot of time helping students get ready to decide whether or not linear regression is an appropriate tool for whatever data set they run into later on. Okay, I'm really out of time. I see some more questions, but I don't want to block everything else. And so here's what I'm going to do. I'm going to declare this the end, but I'm also going to hang out and answer the questions that I didn't answer. So if anyone wants to keep listening, you can, but I will promise not to say anything else. Instead, I left you the slide link, and I will tell you the thing that I always tell students, which is that lecture is not the most important part of this course. It's the lab. So if you want to understand what students do to really learn this material, it's to work through interactive labs, and we're running an interactive lab in another session right now. So if you want to understand what it's really like to take Data 8, go to that. If you want me to answer your question, you can hang out and I will answer your question. And thank you very much for listening. Sorry I went a little bit over time. Okay, back to the questions. Do you find that math computer phobic students are more receptive to this course than typical stat CS courses? Business students, etc. Yes, I think that we get a different distribution of students, and they tend to be drawn more from the campus as a whole. Business students in particular, there's a lot of data science plus econ students out there these days. So there is a set of students out there that is not terribly excited about programming for the sake of building applications or games or whatever, but does get excited about this approach to computing. Where do the data science projects come from in Data 8? I asked students to find the data online, but the projects from students seem too repetitive and done somewhere. We do not emphasize independent projects in this course. Instead, we pick data sets, we set them up with questions that they need to answer, and they go through the work of answering those questions, and that's what we call a project. We have done experimentally some kind of choose your own adventure final projects in the course, and we've found a few of them are great. But usually at the end of this course, there aren't that many students who can find an interesting data set, learn something new about the world just from what they've learned in Data 8 in that like one last week in the semester when they have time to do it. And so, yeah, some of the projects that students did independently where they had to find their own data set and like do the work themselves tended to be just like, oh, I ran the code on this data set and here's what came out. Look at me, I'm done, without a great job of describing what they really learned or concluded from this process. So yeah, so I'm a fan of giving students a more structured data inquiry problem in their first course and letting the open-ended stuff happen in later courses. But leaving it as an option is a good idea because there are a few students who are like really great at it. It's so cool. The central limit theorem is asymptotic, and I said I didn't use asymptotics. I lied. There is the central limit theorem and it's asymptotic. You're correct. Yeah, so I think we never wanted to claim that what is taught in an intro statistics course is not appropriate to teach undergraduates. I don't agree with that at all. And in fact, there are students who take this course and they take an intro statistics course because they just want to see, you know, both perspectives. There's a kind of sampling simulation based version that we do, and the more analytical version that's typically taught in a stat course. And you got to know them both eventually if you want to spend a lot of time in the field. So a lot of Data 8's design is about dealing with the fact that because we're doing computing and statistical inference and real world data all in one semester, we got to pick and choose our battles. But that's not to claim that like asymptotics aren't useful. And so there is a case here where it just seemed like necessary to include it in order to fulfill their education. I don't know if that satisfies you or not, since I'm just kind of talking into my camera here, but I don't know if that was kind of the subtext of your question or not, but that's my take. Okay, so most data sets are not random samples from a population of interest. You might have the whole population or a sample that may or not be representative. How do you handle this? We do actually just try to pick data sets that, well, okay, so two things. One is often we'll start with the whole population. We will draw a random sample. We will pretend that we don't have the population and just work with the random sample. Just to say like, oh, imagine this is all you had. What would you do with it? I think that's useful because then you can refer back to the population and see how it went. So in particular, you can repeat this process many times and figure out what fraction of the confidence intervals that you built actually cover the population parameter that you were trying to estimate. You can't, if you just have the sample, you couldn't do that. But if you had the population, well, all this work that you did was a waste. I mean, you had the whole population, you could just measure the thing that you wanted. But it gives students a chance to understand what would they do if they had a random sample. Yeah, I don't think there are a lot of data sets in the course that are generated from other kind of sampling. I think that's just kind of topic for a later course. The data science module doesn't deal with date time. Why? Well, maybe we just never got there. And data science module needs improvement. That's probably the answer to this question. And if anyone would like to contribute, that would be wonderful. I think that within the context of the course, we don't have a lot of timestamps. We mostly have years. And so those can be kind of modeled as integers, and that keeps life simple. Okay, made it through the questions. Well, thank you so much for all your questions, for the folks who are remaining. That was awesome. And it's been a pleasure. So go to the lab. I'll see you later.